The summer is the best time of the year, right? And a warm shower is also nice. We've combined these two nice things in the exercise of the portable shower using solar power. Welcome. The situation is as follows. We have a large black plastic bag which is a sphere shaped and has a diameter of 50 centimeters in which water can be warmed up by using the sun as an energy source. I have sketched the situation. Question 617. It asks, what is the heat flux on a surface on Earth which is perpendicular to the Sun? Okay, so for this I'm going to draw our Sun Earth system. And then we have here the radius of the Sun, and this distance is S. Then I want to consider a thermal energy balance over a control volume that contains mostly empty space between the Sun's surface and the surface with radius S. So that surface is this one. Thermal energy balance would look like this. We have an energy flow here. And we have a flow out through this sphere. So the balance in principle is very simple because there is no radiation produced in our control volume. So we have that 0 is phi in minus phi out. Phi in is the heat flux at the Sun's surface times the surface of the Sun is 4 pi rs squared. And then similarly for phi out, we have the heat flux at a distance s, and we multiply it with the surface of this big sphere. And then this heat flux is actually the one that we're looking for, because that's the tiny part here. That's the heat flux through the surface over here. Okay, so we isolate this term and we get phi q rad at S double prime, the heat flux, is equal to the heat flux at the Sun's surface times, well, the factors 4 pi will cancel, so we get rs squared divided by s squared, and this I calculated to be equal to 1380 watts per square meter. Where I used Stefan Boltzmann law for the heat flux at the Sun's surface, which is sigma T s to the power 4, and I've used Wien's displacement law to calculate the Sun's temperature. Question 618. The bag is put in the sun and warms up until a steady state is reached. In this steady state, the loss of heat due to convection is 64 watts. What will be the temperature of the water inside the bag? Well, for this, I want to write down the thermal energy balance over the plastic bag. So we have radiation from the sun coming in. We neglect the radiation from the environment. We have radiation going out due to the temperature of the bag, and we have loss due to convection. Okay, so the radiation that's coming in is phi q rad s. So the heat flux we just calculated above times the frontal area of the plastic bag, which is pi rb squared, where I use that rb is the diameter d over 2. Then the radiation that's going out is the heat flux at the surface of the bag times the area that radiates this, and this is just half of the bag because half of the bag is insulated and half of the bag is a black surface. So half times is full area rp squared minus phi cv. Okay, so let's write this one more time. And then, well, because it's a black body, all of the radiation is also emitted due to the temperature, or it radiates as a black body. So we have sigma Tb, which is the temperature of the bag, times, simplify this, 2 pi Rb squared minus sigma Cv. Then we can isolate Tb. This comes out as Tb is rad. So the heat flux at the Earth times pi Rp squared minus the heat loss divided by sigma times 2 pi Rb squared, and this to the power 1/4, and I've calculated this to come down as 37.5 degrees Celsius. Question 619. It deals with a more realistic situation where the surface of the bag is not considered black but gray. What do we expect? Well, because the surface is not black anymore, not all radiation from the sun is absorbed. So with this, we expect that the temperature is going to decrease. However, also, because it's not a gray surface anymore, the emissivity is not 100%. So it will also radiate less energy into the environment. So this might cancel the first effect. However, the loss due to convection, it remains the same. So because the total amount of energy that comes in is less, we expect also that the temperature will decrease. Now, let's look at what's going to happen. We need to consider exactly the same thermal heat balance. We only have to adjust it a little bit because not all the radiation that shines on the back is coming in. So we need to introduce an absorptivity here. Then one line below, not all the bag doesn't radiate anymore as a black surface, so we need to introduce an emissivity here as well. Then in our final expression, this becomes this. So then our temperature is going to come out as 31.3 when you fill in all the numbers. Here I've used that A is equal to E for a gray body is 1 minus the transmissivity minus the reflectance is 0.8 in this case. Okay, let's make some room. Question 6.1.10. The designer changes the design from a sphere to a box to increase the temperature to the level of question 6.1.8. We need to find the height of this box. Okay, so there's a reason I stopped at question 6.1.8 because it looks very similar. So the heat balance, thermal energy balance, it looks quite similar. We have radiation coming in due to the sun. We have radiation coming out due to the temperature of the box. Only still have the same loss due to convection. So then it continues in steady state. We have 0 is so the heat flux due to the radiation of the sun times the area, and that's now a new area, the area of the box I call A. And then we have the heat flux at the box times the area of the box. And now this area, so the area which with which it receives radiation and with which it emits radiation, is exactly the same. So this is different from the previous question. Okay, then so the box also has an emissivity of E, and Stephen Boltzmann's law gives us this times A minus CV. And I forgot that not all radiation that is falling on this box is actually absorbed. So I need to put in the absorptivity like this. Okay, from this I can isolate my new area to be phi CV divided by A phi double prime Q root S minus E sigma T B to the power 4. If you fill in all the numbers, and for TB you fill in the temperature you want of 311 kelvins, I get 0.0942 square meters. Okay, but then we are not there yet because it's required, or we want to find the height, and it is required that the volume of the water remains the same. So what do we have? We have that the volume of the box is equal to the volume of the plastic bag, which is 4/3 pi times RB to the power 3. And then solving this for h, we get 4/3 pi r b to the power 3 divided by r. Area is 0.695. And do note that this is bigger than the diameter of our plastic bag. Question 6.1.11. Okay, comparing frontal areas of both designs. So we have for the box, we have A is 0.09, and for the sphere, we have pi RB squared. So if we compare this, I make the fraction pi RB squared divided by A is, well, the frontal area of the large plastic bag is 0.196 divided by the area I calculated here, and this comes down as 2.1. So the frontal area of the large plastic bag is actually bigger. And this is because the sphere design is less efficient in keeping the heat, because the surface area with which it radiates into its environment is twice as big as its frontal area with which it receives radiation from the sun. Question 6.1.12 is about using the shower as a measurement device on some exoplanet to calculate the temperature of a star. Okay, so we will first look at the similar balance we used at question 6.1.10, this one, because this is, we can use this one straight away. Only we have to change something, because now we have, still in steady state, we have absorptivity, but we have a different flux. That's due to radiation at a sphere that touches the planet Konos. But we have a same surface area, same emissivity, sigma Tb to the power 4 times A minus the same loss due to convection. Okay, then with a similar balance as used for the flux due to the radiation of the sun, you could make exactly a similar balance over empty space between the Omega Leonis star and the planet Konos, and you will get a similar answer, a similar expression. So then you have VQ rad Q omega is VQ rad at Omega Leonis times the radius of Omega Leonis squared divided by the distance between Omega Leonis and the planet Konos squared. It's exactly a similar expression. Now I can put this in the balance of above. So then we get 0 is A times VQ rad omega prime R and the rest is straightforward. Using Stefan Boltzmann law, we can introduce the temperature of the planet, of the star Omega Leonis, and now we can isolate this temperature, and we get T omega is E sigma TB to the power 4 A plus V convection divided by A capital A sigma R W squared, the radius of the star, and this all to the power of 1/4 is the temperature. And if you fill in all the numbers, including the temperature TB measured of the box, the temperature of the box, I get 6020 Kelvin, 6020 Kelvin. From Kronos back to Earth. That's it for this exercise. Travel to the forum for your questions. Good luck on the rest of your journey.